Today we are going to talk about cutting tools. Well, when there is a talk of manufacturing and machining, we need something in order to take the cut from the material. And in conventional and traditional processes, machining processes, it's the cutting tool which is taking the cut and removing material from the workpiece. It's important to know what is the right cutting tool for a given machining operation. There is a large variety of cutting tools being used in industry. Thousands of cutting tools, different types of materials, different geometries of cutting tools. And for the one who is familiar with basics of manufacturing methods and machining operations, it's necessary to have a basic knowledge on different types of cutting tools. Particularly if you are working as an engineer in an industry, you've got to have a basic knowledge on different types of machine tools which differentiates between you and the simple machinist. Does it make sense? An engineer is expected to know much more than a simple machinist. Okay? So in today's lecture, we are going to improve our knowledge and extend our knowledge on, say, cutting tools and cutting tool materials. And we will be trying to establish a relationship between the material and also geometry of the cutting tool and the machining operation. It's good to know that about 50% of cutting tools are not being used properly in industry. About 50% of the machining operations, cutting tools are not used properly, which results in what? In yes, and increased cost of tooling, plus reduction in profitability and reduction in productivity. So if we know how to make use of the cutting tool properly, we can significantly reduce the cost of machining and also improve profit. That's what we are after, right? Every manufacturer is after increasing productivity and profitability. Well, and one of the most important topics in this lecture is tool life. What is the right tool life? When we make use of the cutting tool properly, it should achieve its designated and designed tool life. If we don't make use of it properly, then we will reduce its tool life. Its life. The life of the tool will be reduced, and as I said, we've got to replace the cutting tool. When we are replacing the cutting tool, then we've got to pay for the time of replacement of the cutting tool first, for the time when machine is not being used, because we've got to replace the tool. It's not making the money. And once the cutting tool is replaced, we have already paid for the new tool, which is now being used, despite the fact that if we had used the previous tool properly, still we were using the older cutting tool, which would reduce our cost eventually. Okay, if we are interested to know more about cutting tools, in case we are an engineer in industry in the future, hopefully in the near future, and we work for industry and we need to know much more than what we have covered in this lecture, the textbook which I have put in this slide provides us with a lot more information on cutting tool technology, proper machining operations, and how to choose the right cutting tool. So it's a good reference for your future, or in case you want to do a project or something on cutting tools, this could be a useful textbook to be used for this purpose. Well, inserts. Here in this slide we can see different shapes of inserts which are often used in cutting tools. Generally, we can divide cutting tools into different groups. One of the most commonly used cutting tools, a group of cutting tools is high-speed steel cutting tools, HSS. Have you heard of HSS cutting tools? High-speed steels. In high-speed steels, we don't make use of an insert because the whole material is of high quality and it is the one to be used for cutting the material. However, high-speed steels cannot be used for really hard material, for cutting really hard materials. If this is the case, then we've got to make use of inserts. We've got different types of inserts. Some of them are shown here. We've got, say, for example, carbide inserts, ceramic inserts, cermets, etc., etc. Each of those inserts provide us with different set of properties in terms of, say, for example, hardness, toughness, geometrical shape. And depending on the type of the material being cut, we've got to choose the right type of insert. Some of the inserts are actually coated in order to improve properties such as resistance to wear, and some of them are not. Of course, again, it depends on what we are after, and if the insert is coated, it does increase the cost of production of the insert as well. And in the discussion of cutting tools, there are two important factors to be taken into consideration. The material, what is the material of the cutting tool, and its geometry. And each of those two parameters do play an important role in what we get in the end. When we are talking about cutting tool materials, we are often after a certain type of properties. Like what? We want to choose the right material for the cutting tool. What is important to us when we are choosing the material for a given cutting tool? Yes? Say that again, please.
What is to be used for?
To cut a certain material.
Yeah, that's what I mean.
So what you mean is that what is the material to be cut? That makes a difference. But what I'm asking is, in general, what we are after is a certain type of cutting tool when we are going to choose a type of material. What are the properties that we are after as a whole? Hardness. Hardness. If a cutting tool material is not hard enough, it can take the cut from the material. That's very obvious, right? What else? Ductility. Ductility, is that what you mean? Sometimes ductility is of actually importance in the selection of the material, but not always. As we know, ductility and hardness are inversely proportional. When we increase hardness, we are sacrificing what? Ductility. If you increase ductility, then you are lowering hardness. And more often, in cutting tools, we are after a high hardness rather than ductility. What ductility does provide us is actually ability to deform, which isn't desired in cutting tools. Instead of ductility, we may refer to something else, which is called toughness. Toughness is more important than ductility in cutting tools. Okay, which is defined as resistance to fracture. That's important. Okay, what else? Rigidity, which is directly related to hardness. What else? What's that? Roughness. Well, that's something which is decided, yes, by the geometry of the workpiece, yes. That's relevant to geometry rather than the material. Inertness. We don't want to see the material of a cutting tool which is actually making a chemical reaction with coolant or the workpiece itself. And hot hardness is another property which is of interest in cutting tools. What does that mean? When the cutting tool is really hot, because it is taking the cut and temperature increases significantly. At that elevated temperature, a cutting tool has to maintain its hardness at elevated temperature, which is referred to as hot hardness. Still, we can add more. This is just a discussion of cutting tool materials. How about geometry? Geometry also plays a significant role in any machining operation. In last week, we had a discussion on the theory of machining. We remember the rake angle and the shear plane angle. Those are some typical, actually, parameters which are decided by the geometry of the cutting tool. So, geometry also could play a role in the tool life and also in the outcome of the machining process. Like what you just mentioned, the roughness. Some of you will be doing in the lab, some of you will be working on the lathe, right? Measuring the surface roughness on a turning machine. How many of you have done that? Many of you already. What are you after in this, say, task? Resultant surface finish, which depends on what? Machining parameters and also and the geometry of the cutting tool, which is the tool nose radius, right? So, as you can see, what you get to some extent depends on the geometry of the cutting tool as well. So it's important for us also to make use of the right geometry for the cutting tool in order to achieve proper outcome. And there are three modes of failure of the cutting tool. What I'm going to ask you now is that which one of these three, which are listed here, fracture failure, temperature failure, and also gradual failure, which one is the one we are after? Which one? Gradual. Not the other two. I would say none. None of those are desirable, right? Because we want to have a cutting tool which works and lasts forever. However, unfortunately, we don't have that technology at this time at least. So we've got to choose one. And if this is the case, what Brock said makes sense. Meaning that we are after gradual failure if the cutting tool has to fail, which is the case. Why we are not interested in the first two then? Fracture failure when the cutting tool breaks due to excessive loading, excessive machining forces. And why we are not interested in the second one, which is temperature failure, where cutting tool fails due to excessive heat, which is generated as a consequence of machining. Say that again? Well, you can say so. Indeed, the first two modes of failure, which is fracture failure and temperature failure, are referred to as premature failures, meaning that the cutting tool can still last for some time if it doesn't fail. But we make the cutting tool fail because we have not used the cutting tool properly. We are lowering the tool life of the cutting tool and making it necessary to replace the cutting tool. By doing this, we are increasing the cost of tooling, which isn't desirable. If a cutting tool is used properly, after its designed lifetime is passed, the cutting tool has to be replaced. Otherwise, it does have a negative impact on the result of the machining operation. For example, the surface finish will not be what we are after. And the productivity will be reduced. And the magnitude of the cutting forces will increase. And as a consequence, we will move away from optimum machining parameters. So it's the time for us to replace the cutting tool. Now, here we've got a number of pictures showing us the way that a cutting tool is worn when it is being used in a machining operation. As we can see, when a cutting tool is being used, for example, this is a single edge cutting tool which is often used in operations such as turning. As you can see, there is a type of wear which occurs on the top face, which is the rake face. And a depression is formed right here. And there is another type of tool where it happens on this face, which is referred to as flank wear. And when you make use of the cutting tool for the very first time, any of these two types of actually wears do occur on the cutting tool. However, is everyone listening? Could I have your attention, please? Excuse me. Excuse me. Take your headphone off first, please. Okay, please do not disturb other people, okay? Thank you. Well, anyway, these two types of wears do occur on the cutting tool, and eventually, after some time, we've got to replace the cutting tool with a sharper cutting tool when it's the time to. And here you've got a microscopic image of the two types of wears. In this type of wear, which you can see here, which occurs on the top face or the rake face of the cutting tool, there is a region which is worn. You can see it if you take a look to the cutting tool. When you go to the workshop this time, take a look at the cutting tool to see if you can actually identify this type of wear and also the other type of wear, which is flank wear and also crater wear on the tip of the cutting tool. And this wear continues as long as this region, there is still a slight edge left here. As soon as this edge is removed, it's the time for us to replace the cutting tool, because it does produce scratches on the surface of the workpiece, which isn't desirable. Well, and in order to actually increase the tool life of the cutting tool, again, let's go back to the three modes of failure. If we want to prevent the first type of failure, what do? Which is fracture failure, which results as a consequence of excessive, say, cutting forces. What do we do in order to lower the magnitude of the cutting forces? Yes? That could be also a choice. But first of all, if we don't want to change the material of the cutting tool or the workpiece, how can we lower the magnitude of the cutting forces? Yeah? Yeah? Which is lowering the depth of cut, which is right. Lowering the depth of cut will lower the resultant cutting forces. And what else? Feed rate. Lower the feed rate, which plays the same role. Because we are lowering material removal rate. By doing this, we can increase the tool life of the cutting tool and also prevent fracture failure. The other possibility would be to make use of a different geometry of the cutting tool, which is stronger, so that it doesn't fail. Let's talk about the second type of failure, temperature failure. Cutting tool fails because of elevated temperature, which makes it softer than necessary in order to take the cut. How can we prevent this type of failure? Say that again. Yes, reducing cutting speed would lower the temperature and Making use of coolant, yes, would do the same job. And what else? Lowering the feed, again. Lowering the feed rate. Okay? And the other possibility, if it is possible, is to make use of a different type of cutting tool which has got a higher grade of material, which is still hard enough at that elevated temperature. And number 3, how can we increase the lifetime of the cutting tool to make it last longer when we are referring to gradual wear? Again, by lowering cutting speed and feed rate as much as possible, we can increase the life of the cutting tool. However, please note that in doing so, we are also lowering productivity. So we've got to compromise between productivity and tooling cost. Okay? If we lower the cutting speed and also feed rate, you can increase the tool life of the component. However, would that be profitable if you make just a few parts per day to make your cutting tool last a really long time? It won't be economical. So we've got to compromise between the two, which is referred to as optimization of machining parameters. What does this mean? It means to find the optimum value for the machining parameters, when you can still make money and also you are watching, you are keeping an eye on the cost of tooling. So always we've got to find the right combination of the two. Okay. And here in this curve we can see a representation of the tool life on the basis of flank wear and also the life of the cutting tool. As we can see here, it's divided into 3 regions. Here we've got time of cutting, and on the vertical axis we've got flank wear, which is presented in the previous slide. In the very beginning, as you can see, there is significant wear on the cutting tool when the cutting tool is new. As it is touched, the coating of the material, the coating of the cutting tool on the nose of the tool will be removed instantly. And after this, there is a long period of time during which the tool, the slope of the line which is presented here is constant. It doesn't change. It's steady. And this is indeed a useful time of the cutting tool when it is being used in order to take the cut. And then after this period, which is beyond the steady state wear region, we've got failure region. As you can see, flank wear increases significantly, and all of a sudden, at this given point, the cutting tool fails. In industry, we've got to make use of the cutting tool, starting from here all the way up to here, and replace the cutting tool before it fails. Before it fails. Because if it fails, it may do what? It may have a negative impact on the surface of the very last part, and that may actually scrap the part. Maybe you lose a part because of the bad cutting tool which has been used to make it. So we've got to replace the cutting tool before it fails, which is right at this time, somewhere here, which can be computed. When is the time to change the cutting tool? Before it fails. Okay, and here we've got a slope for this region, which is steady state wear region. There is, as you can see, there is a slope. And there is a machining parameter which decides about the slope of the curve in this region. What's that parameter? Which is deciding about the slope of the line in this region. What's that? There is a number of parameters, of course. Which one is the one which has the most important role in deciding the slope of the line of the curve in this region? Which one? Cutting speed. Good answer. It's the cutting speed. Meaning that if we increase cutting speed, what happens to this line? What happens to the slope? Would that be increased or decreased if we increase the cutting speed? Yes, it becomes steeper, and eventually, if it moves up like that, we reduce the lifetime of the cutting tool significantly. Let's take a look at this slide here, which is telling us more about this. It's the same type of graph where we've got tool flying well and against time of cutting. And as you can see, when cutting speed increases to 160, the lifetime of the cutting tool reduces to a very short time. For this given case, it is only 5 minutes. For this one, where we've lowered the cutting speed from 160 to 100, the cutting tool lasts for 41 minutes. So as you can see, it's the cutting speed which plays the most important role in deciding the life of the cutting tool. However, you can improve productivity. Often, somewhere between these two extremities is the one which is of interest in manufacturing processes. Okay, now I'm going to ask you a question. I would say by now, you absolutely know the answer to this question. Let's see if you can do it. Which one of the following machining parameters, which are cutting speed, speed, depth of cut, or coolant, has the greatest effect on the life of the cutting tool? Which one is it? Coolant. What else? Which one? Cutting speed. Coolant, of course, has an impact on this, but if we take these parameters into consideration, the number one parameter which plays a role in the life of the cutting tool is cutting speed. Look, if cutting speed increases, this is representing the tool life. The tool life is decreasing significantly. If we increase feed rate, that also reduces the life of the cutting tool. However, the impact of this one is greater than the feed rate. And the other two parameters, which are cutting depth and also coolant, they will have an impact as well. But the effect of cutting speed is greater than the other three which are listed here. Okay? This is a mathematical model showing us how these parameters do affect the life of the cutting tool. Okay, so these three which I have listed here, depth of cut, feed, and also cutting speed, are the ones which decide on productivity. How do we choose the right range or the right value for each of these three parameters for a given machining operation? We are machinists, or we are deciding about machining parameters to be used by the machinist, and we want to know how to assign right machining parameters which are listed here for a given machining operation.
We can find VMAX and VMean and choose the parameters.
On the basis of what? That is right. For Vmax and Vmean, there is a range. Which one is the right value for that cutting speed within the range? How do you decide?
Optimal point between speed and material.
Correct. We've got to find the optimal values. However, optimization is a time-consuming task. Not everyone can do it. If we want to just choose the right machining parameters in a short period of time, what's the rule to be used in order to decide these parameters? I'll tell you how to do that. Let's decide about feed rate. We want to machine a part and we want to decide about feed. How do we do that? In industry, people do it this way. They choose the highest feed, which can give us the result, the required surface finish. We know that it's the feed rate which decides the surface finish, the most important parameter, I mean. So choose a feed rate which is maximum and is still giving you desired surface finish. Does that make sense? So we've got maximum productivity, still we've got desired surface finish. Let's move on to depth of cut. How do we do that? We have decided about feed rate. How do we decide about depth of cut? The rule to be used in industry is take the deepest cut, which is allowed by the power of the machine and also rigidity of the machine tool, and work this. The deepest cut, which is possible. And about the last machining parameter, which is cutting speed. How do we decide cutting speed? Cutting speed has a direct relationship with tool life. That's what we had in the previous slides. Okay? The rule in industry for selection of cutting speed is choose highest cutting speed, giving you desired tool life. For a given tool, the desired tool life is given by the manufacturer of the cutting tool. What is the highest cutting speed which gives us desired or designed tool life? That's the one. So 3 simple basic rules in order to decide each of these 3 machine parameters. If we do not want to actually make use of optimization methods and that sort of stuff. It's the way that machinists in industry decide about machine parameters. Okay? And here we've got a table which is taken from a machining handbook. And as you can see in this table, there is a range introduced for the cutting speed. There is a range which is introduced for each of the cutting speeds. As you can see, for example, if we are making use of high-speed steels, depending on the type of the material being cut, we've got to make use of the right cutting speed. And the range of the cutting speed is given here. For example, we are cutting alloy steels, and we are making use of high-speed steels. For alloy steels, the range of the cutting speed is between 20 to 37 meters per minute. Now the question that I asked before is again, what is the right value of cutting speed within this range? How do we decide that? How do we decide about the exact value of cutting speed within the range of 20 to 37? It depends on the policy of the manufacturer. You are the manufacturer, right? Right now, suppose that you are the manufacturer, and you want to decide about the right cutting speed. What would you choose? What would you do? Which one would you choose?
It says that there's a range of values too. It says that the hardest one. It says it goes from 1320 to 1962. So, sorry, 9262. So it depends which one of these steels you're using. If it's a harder one, you use the lowest rate.
Yeah, so let's say this one then. Mild steel. 38. You would go for that one. But as I said, I'm not saying it's incorrect, but there is a better way of doing it. It depends on the policy of the manufacturer, which is you. Do you want to make more parts, or you want to lower the cost of tooling? Which one is your policy? Or maybe something between the two. In general, there are 2 different approaches. If we are making use of productive machining parameters in order to increase productivity, meaning that you can sell as many parts as you make. So if you make more, you make more money. If you produce more parts, you make more money. Then you make use of productive machining parameters, which is represented in this curve. And we've got cutting speed and against unit cost. What is unit cost? The cost of machining a single part. It's called unit cost. And here we've got cutting speed. Again, we've got another criteria which is called economic machining parameters. Now, situation is totally different, meaning that there is no buyer in the market. So if you make more, there is no one buying your part. So it's better to lower the cost of tooling as much as possible and still make a number of parts to keep the company running. Depending on the circumstances, which could be different at different times. For example, today, economy is no good, we know that. Economy is no good. In 10 years' time, maybe it's really good, or in the past it was good. So the policy of the company changes depending on the economy of the country or some other parameters. If you want to make money on the basis of high production, then this is the one to be used, otherwise that's the one to be used. And for each set of these, there is a minimum. Take a look at this curve. The minimum machining parameter, the minimum cost, minimum unit cost occurs somewhere here, giving you some value for V. If you are making use of economic machining parameters, the minimum V will be something different, resulting in minimum cost, which is indeed defined as CP, which is minimum unit cost when we are making use of productive machining parameters, or CE, giving us minimum unit cost making use of economic machining parameters. And the range of useful cutting speed always lies somewhere in between the two. So the cutting speed should be chosen something between VE and VP, which gives us a tool life which is different. If we represent tool life, as we increase cutting speed, tool life decreases. That's what we had in the previous slide. So, cutting speed should be chosen something between VE and VP, giving us a tool life between TE and TP. So, depending on the circumstances, we've got to choose the right one. Does it make sense? In any given time, V is always between VE and VP. When economy is really good, VE tends to be closer to VP. When economy is really good. When economy is bad, it moves back towards VE. But it is always moving somewhere between the two values of VE and VP. Okay? That's a very basic actual knowledge. If we want to do more, we've got to develop a program, do the optimization, etc., etc. But this is something which can be actually computed easily. It doesn't take long for us to have these computed. This is what you refer to, right? Something similar to this. Okay? Is it clear to everyone? Okay, now we have got an idea about how to choose different machine parameters. And there is a very important equation in this slide. Indeed, I have only two equations for this section, and this is the most important equation. And it's a very short one. So it's easy to remember the equation itself, which is, this is a very well-known equation in machining, referred to as Taylor's full life equation, defining a relationship between cutting speed V, T, which is tool life. And in the equation we've got N, which is tool life exponent, and C, which is the constant value. The value of N depends on the quality of the workpiece, of the cutting tool material. And in the table below, as you can see, in the table below, the values of N for different types of materials for cutting tools are given. If we are making use of high-speed steels, the value for N will be something between 0.08 and 0.2. For carbides, it is something between 0.3 and 0.5, depends on the quality of the material. And C, which is a constant value, is also defined as the cutting speed, giving us a cutting speed of 1 minute. C is defined as the cutting speed, giving us a tool life of 1 minute. So this is a very important equation helping us to decide the right value of the cutting speed, giving us the tool life which is desired. How do we make use of this equation then? The manufacturer tells us that the lifetime of the cutting tool which is purchased from the market, say for example 50 minutes or 1 hour is the life of this cutting tool. Then put all the parameters into the equation. When you have T, you can easily compute V on the basis of T, right? Yes or no? Yes. Okay, we will have a problem to see how to do it. Is it the time to take a break? Not yet, okay. So we can do the problems. And take a look at this slide before I move on. Tool life, cutting speed. It's telling you something. What is it telling you? You increase cutting speed if you want to lower the life of your cutting tool significantly. And also please note that if you increase this just a little bit, this will have a big impact on the life of the cutting tool. Do you remember the previous slide that I had? For a cutting speed of 160 meters per minute, the life of the cutting tool was only 5 minutes. We lowered the cutting speed from 160 to 100, which resulted in an increase of the tool life to 41 minutes. So the difference that cutting speed makes in the life of the cutting tool is really, really big. And here we've got a table telling us about the values of N and also C for different types of cutting tools, which I have taken from the textbook. Table 21.2. And this table will be used in doing one of the problems. That's the reason that I am showing this to you. Okay. Let's take a look at this example here. Well, we have to determine the values of C and N in Taylor's two-law equation. And the equation is given up there. In the plot, using 2 of the 3 points on the curve. There is a curve here, establishing a relationship between values of cutting speed and tool life, V and T. And it is linear in this log-log plot, as you can see. For a cutting speed of 160, tool life is 5 minutes. For 100, it's 45 minutes. It's the same problem example that we had in the other slide. And when cutting speed is 130, tool life is 12 minutes. So if we connect these points to one another, we can draw a straight line connecting these points to one another. So the relationship is very obvious. Now, we've got the Taylor's equation, which is given up here. What we are after is to determine C and N for this given equation on the basis of the information which is given here to us. How can we do this? Forget about the table that we had in the previous slide. On the basis of the information given here, we are to determine C and N. How can this be done? Can you work with your partner, someone sitting next to you, spend a few minutes on this before I provide you with a solution to the problem? This is the whole information given, only this slide, nothing else. The whole information given to you is this, is here, equation, Taylor's equation is given, and you've got to compute the value of C and N for this given problem. So you've got to do at least one problem in order to learn how to do the problem. If you do it once, then you know what to do. And it's not as easy as it looks. It's a little bit challenging, okay? So you've got to know how to compute the values of A and C. If it is easy, then you know what to do. And then you have not a problem for the very first time, then you know what to do. Otherwise, it will be challenging. You need a calculator with you if you are doing the problem. Have you got calculators with you, everyone? The unique part of it is computation of n. When n is actually computed, the computation of c is just straightforward. Have you made any progress, anyone? Have you made any progress in doing this problem? Well, would that help? Let's see how we can do the problem. Is there anyone who has done the problem so far? Anyone? Yeah? Okay, let's see how to do it. Indeed, this is the equation of Taylor which is given. If we make use of the two extreme values for cutting speed and tool life, which was 160 for cutting speed, giving us a tool life of 5 minutes, and 100 meters per minute, giving us a tool life of 41. All these can be written in this form, in the form of the Taylor equation, right? Yeah? And we know that constant value means that the value of C, which is defined as the cutting speed giving us a tool life of 1 minute is the same because material has not changed and cutting tool has not changed. So the value of the C remains the same. That's why it is called a constant value, right? For the two operations. If this is the case, can we equate these two equations to one another to write it in this form?
Yes.
It should be equal because they are both equal to C, right? Now, does this give us a clue on how to compute the value of n? Because there is only one unknown in this. How do we do that then? We write it in this format. Well, now it's a tricky part of it. How can we compute the value of n because it's in the power? How can we compute the value of n then? Well, natural logarithm. If we take the natural logarithm of both sides of the equation, then it becomes easy to have it computed. Taking the natural logarithm of both sides gives us this equation. Right? Right? Or wrong? It is of course right, otherwise it wouldn't be there. It's right. If we record how to take natural logarithms, then it's easy. If you take natural logarithm of this, then it becomes natural logarithm of 160 plus n times natural logarithm of 5, which is this. Same to the other side. Now, it's not hard to compute the value of n there. If this is written in this form. It's not hard to have these computed. Okay? That was the tricky part of it. Now, n is computed. When n is computed, how do we compute C? How do we compute C? Yeah, it's very obvious. We've got n, we've got everything else. C can be computed easily. C can be computed easily by making use of either this equation or that one. It doesn't make a difference which one to use. Then it gives us a cutting speed of that much for a tool life of 1 minute. You want to be sure? Okay, check it with the other equation. It should be equal to in these equations. The value of the two equations should be equal to this given value of C. And then we have computed the value of n and also C for this given machining operation. It's not hard, is it? It's not hard. It's just like that. Then you know what to do. Easy one. If it is in the exam. Okay? I'm telling you something, okay? If it is in the exam, easy mark. It means that it's possible that you see such a problem in the exam. So it's good to learn how to do it. Okay. How about doing another problem? Let's take a break first, okay? After the break, we'll do another problem to be sure that you know how to do this type of problem. Okay, let's go to the next one. Start with one now. Okay, so in this problem, by substituting the values of V and T, V1 and T1 in Taylor's two-life equation, as I said, regardless of the value of N, we can compute the value of C in meters per minute, which is 240. First step of the problem. Now we are after the value of N, having C at hand. How do we do that?
N is 0.231.
Say that again, please.
0.231.
Yes, that's correct. How do we do that, everyone? Computation of N, having C at hand. In case 1, because the value of T is 1, we can't compute the value of N then, on the basis of that. Because N is playing almost no role. So we've got to take into consideration what is given to us in this for the second operation, which is giving us a tool life of 20 minutes for a cutting speed of 2 meters per second. Okay? Having this converted into meters per minute is equal to 120, substituting values of V and T, V of 120 and T of 20 minutes gives us the same value for C, because same material and same cutting tool is being used. So the value of C here is equal to the value of C here, right? Material hasn't changed, cutting tool hasn't changed, so same C is in place. So having this at hand, we've got 2 to the power of A is equal to 2. And by taking the natural logarithm from both sides of the equation, it's not hard to compute the value of N, which, as you said, is equal to 0.2314. And the last part of the problem, having N and C at hand, we have to compute the value of T for a cutting speed of 1 meters per second. First, convert it into meters per minute. Okay? Once this is done, which is equal to 60 meters per minute, substitute the value of T, value of V in Taylor's equation. We know the value of N, we know also C. The only unknown value in this equation is now T, giving us a tool life of 400 minutes. 400 minutes. Which is huge. A huge improvement in tool life by decreasing cutting speed from 4 minutes to 1 minute. It's 25% of the original value, the value of V, and tool life has increased from 1 minute to 400 minutes. Wow. It's 400 times more, isn't it? Cutting speed has been reduced to 25% of the original value, and tool life has increased 400 times. It's a huge improvement, isn't it? I have worked in industry, and I know this is important to know these very basic things. It's very important. I remember that I was the manager of a production line in a company some time ago, long time ago indeed. And I had a machinist who was making use of too many drill bits per day, too many of them, saying that they are all broken or worn, I've got to replace them. Because he didn't know what is the cutting speed, what is tool life, and whatever. But what he really needed was 4 or 5 per day. He was using more than 20. That was happening, and things like that happen. So if you know these simple things, which is really simple to you as an engineer, it can make a big, big difference to your company. If you don't know, whatever, you just turn on the drill and make the holes. You don't know whether what you are doing is actually economical or it is not. You know that you are making the hole, and that's all. So it makes a difference. There should be a difference between an engineer who knows something about theory and the one who doesn't know anything about theory and only knows how to make the hole. That makes a difference. And this is part of the task that you are doing in the workshop as well. I'm asking you to play with machining parameters and that sort of stuff in order to get a proper understanding of the role that machining parameters play in what we get in terms of surface finish, tool life, etc., etc. Okay, how was this problem? How was the problem? Are we able to do a similar problem again, another similar problem? I don't think we are going to do another one, but we will do some more next week in the tutor session, okay? Nature of the problem is not different. All you need to do is the Taylor's equation and just play with those numbers which are given to you. Okay, now what I'm going to do is to play a video clip on cutting tools before we continue with what is left of the lecture. In this video clip, we will have a talk on cutting tool materials and failure modes, which I explained briefly. We don't have the voice.
Reamer apps.
What's that? No, I think you hear me, don't you? They must have done something to this adjustment of the system. I don't know why you are not. Okay. Okay, let me restart, okay?
Tooling incorporates thousands of different cutting tools and tool holders for discrete parts manufactured. Principal categories within cutting tools include single-point cutting tools, such as lathe tools, multi-point cutting tools, such as milling cutters, drills, reamers, and taps. Cutting tools are either standard tools, which are purchased as catalog items, or special tools, which are designed and built for a special machining job, often to suit a particular workpiece. The main objective in the selection and application of cutting tools is to safely machine the workpiece in the shortest possible time while meeting the part's quality requirements. Furthermore, the specified tooling should be the least costly and least complex tooling available to satisfactorily fulfill the qualitative and quantitative workpiece demands. It is estimated that nearly 50% of all cutting tools are used incorrectly. Additionally, the number one error when formulating tooling selections is calculating monetary savings based on lowest cost per tool rather than on maximized productivity and extended tool life. To effectively select tools for machining a part, a machinist must have specific information about the workpiece, such as the starting and finished shape, the hardness, the tensile strength, and abrasiveness of the material. These factors all influence the interaction between the tool and the work. The machinist also needs to know whether the workpiece material breaks into short chips easily, or whether it tends to flow into long, hard-to-break stringy chips. Also important is the part's work-holding setup, which properly orientates and holds the workpiece, and the power and speed capacity of the machine tool. Changes in the workpiece material, part tolerances, geometries, and quantities required often demand corresponding changes in the tool materials and/or tool geometry selected. For the wide variety of machining applications, there is a corresponding necessity for different cutting tool materials. The ideal cutting tool material should be harder than the workpiece it is cutting, be able to retain its hardness and stability at high temperatures, resist wear and thermal shock, be impact resistant to withstand the mechanical shocks of milling, and also be chemically inert to the work material and the cutting fluid. No single cutting tool material incorporates all these qualities. Instead, trade-offs occur among the various tool materials. For example, materials with excellent chemical and thermal stability, such as ceramics, tend to be brittle, with limited resistance to mechanical and thermal shock. These variable properties take place both within a material class, such as different grades of carbide, as well as when comparing different classes of tool materials, such as high-speed steel and carbide, or carbide and ceramics. All cutting tools have a working life, and then they dull, fail, or fracture. For this reason, they are called perishable tools. The cutting tool life cycle may be a single use or involve indexing to multiple edges, as with an insert, or multiple resharpening, such as with drills, end mills, and taps. It is a safety hazard to run any cutting tool until it breaks. This creates scrap, impacts tool and part costs, and reduces productivity. Aside from breakage, Cutting tools wear in many different ways. Edge wear and flank wear are both a normal and slow type of tool wear. In carbide turning of steel, it often occurs after 15 to 30 minutes of cutting. If the work material is highly abrasive, such as with certain cast irons, this type of wear will accelerate. To correct this problem, select another more abrasion-resistant tool grade. Cratering, or top wear, behind the cutting edge occurs commonly in machining long chipping steels from abrasion and diffusion wear. If the crater grows large enough and contacts the cutting edge, the tool fails immediately. To combat cratering, use hard grades of carbide with tantalum carbide or titanium carbide and hard coatings such as aluminum oxide or other materials such as ceramics or ceramics. Chipping on a tool edge is an unpredictable form of tool failure. It is sometimes started when a high point on an edge breaks away. A stronger carbide grade, different edge preparation, or lead angle change may eliminate chipping. A built-up edge is a deposit of workpiece material adhering to the rake face of the insert. Chips weld themselves to a cutting edge. Sometime later, the deposit breaks off and pulls small pieces of carbide out of the edge. This occurs at or just behind the edge. Ductile materials such as low-carbon steel, soft aluminum, and copper cause this damage. Higher rake angles, faster cutting speed, and higher pressure cutting fluid all help eliminate built-up edge. Deformation takes place at very high temperatures, 1800 to 2000 degrees Fahrenheit. These temperatures cause the insert binder material to soften, depressing the top surface and mushrooming the sides out into the clearance angle, where it is abraded away. Deformation is difficult to detect without the use of a microscope. A deformation-resistant grade and/or high hot hardness coating is required, or else reduce the operation speed to reduce the heat. Thermal cracking occurs when inserts go through a rapid heat-cool cycle, such as in either interrupted cutting or when the coolant is improperly applied, suddenly cooling a hot insert. A notch at the depth of cut line may occur in machining high-temperature alloys or with any very hard outer layer, such as in a casting or forging. This is caused by the pullout of small particles of tool material at the flank, face, and cutting edge by the pressure welding of work material to the tool material. An edge preparation on the insert and an increased lead angle may decrease notching. These are only some of the natural causes of tool wear. Maximum tool life can be achieved through selecting the proper insert or tool material or altering the cutting conditions.
Okay, I assume it was an interesting video clip, wasn't it? Okay, so something that we've got to remember out of the problems that we've had so far is highlighted here. And we've got to keep this in mind when selecting a cutting speed. A higher cutting speed significantly reduces the life of the cutting tool, significantly increasing your cost of tooling. Okay, so when we are choosing machining parameters, we should always keep this in mind. Well, another question. Can you guess the lifetime of Taylor's tool life equation? When was Taylor's tool life equation, which we have used in doing the previous problems? When was that introduced for the very first time by a person named Taylor? Not this equation, the previous one. Any ideas? 20 years? 40 years? 20 or 30s? Okay. It's just over a century when it was introduced for the very first time. It was introduced in 1906, which is 107 years ago, right? Yeah, the equation of Taylor was introduced in 1906, which was published in a research paper in American Journal of Mechanical Engineers, and it's been in use since then, 107 years. Of course, Taylor is not living anymore, but the equation that he has introduced or has given as a gift to engineers and machinists has been a big gift being used since then. There are so many people doing research on machining operations, and trying to introduce more useful equations relating cutting speed to tool life. However, Taylor's equation has been the most well-known and widely used equation since then, because it is very easy to use. By the way, it provides a very good relationship, useful relationship between cutting speed and tool life. Some people argue that it's not only the cutting speed which decides the tool life of the life of the cutting tool. Is this a valid comment? It's not only cutting speed. So why do we define an equation which determines tool life on the basis of a single parameter, which is cutting speed? Yep. And as a consequence, some researchers did introduce a number of other equations, taking into consideration other parameters having an impact on the life of the cutting tool. And on the screen, you can see one of those extended tool life equations, taking into consideration some other parameters, such as, for example, other than cutting speed, some other, say, parameters, such as feed rate, cutting depth, hardness of the workpiece material are also taken into consideration. Still, you can name some more. And they have introduced more equations which are referred to as extended tool life equation. One of them is here. Still, there are some more published in the literature. And for each of those, there is an exponent. There is an exponent depending on the nature of the operation. And all this is equation to a value, a constant value times some other parameters which are referred to as reference values. Of course, this gives us a more accurate equation taking into consideration more parameters than just a single cutting speed. However, is everyone listening? However, most engineers and machinists don't like this equation and still rely on the simple Taylor equation. How about you? Do you like this equation more than the other one? Which one is the one that you like it more? The first one. Same applies to every engineer. When they look at this equation, they just don't like it, simple. Because there are too many parameters in this, making computation and making use of this equation more difficult. You've got to take into consideration so many constant values, exponents, etc., and it takes a lot of time for you to work out the life of the cutting tool. However, the simple equation of Taylor, it's good enough in order to be used for general applications. So we don't go for it when we don't feel the need, right? We don't feel the need. Still, Taylor's equation is good enough, and that's what I'm asking you to do in the problems of this unit. That's why I did include only that one in the equation sheet and not this one. But it's good to know that there are extended equations available in case we are interested. Okay, so let's thank Taylor for doing this really good job, and he did develop that equation after doing so many experiments, trying to relate the values of cutting speed to tool life. Okay, there is a little bit of reading which I am leaving it to you, and there is a little bit of talk about properties of the cutting tools and coolant and that sort of stuff which I am leaving it to you. So I would like to thank you for your participation in this lecture, and